Welcome to Spring LIB.
Let's call big omega the set of functions omega from z plus to the set 0, 1 all the way up to 9. By exercise 38, omega is uncountable. Then we also call P the set of all computer programs, and by exercise 37, P is countable. Now we define function little omega to be computable if there is a computer program, let's call it little p in big P, that computes its values. So recall that omega is just something that takes a positive integer and returns a value from 0 to 9. So this function omega is computable if there is a program P that takes as input a positive integer and returns a value from 0 to 9. And of course, this value must be omega of the input. Now let's assume by contradiction that every function omega is computable by some program, let's call it p omega. Of course, the program does not need to be unique, but we just assume that there is at least one program pw that computes omega. Now we define a map f from big omega to big P that maps every function omega to one computer program p omega that computes it. This map is injective because if f of omega is equal to f of omega prime, that means that the computer program p omega and p omega prime compute the same values. And because the output values of the program p omega and p omega prime are exactly the values of omega and omega prime, and they are equal, then omega is equal to the function omega prime. Alright, so this map f is injective, and therefore the cardinality of big omega is lower or equal than the cardinality of p. But p is countable, so its cardinality is exactly the cardinality of z plus. But also, well, so omega is countable because its cardinality is lower or equal than the cardinality of z plus. But we know that omega is uncountable. And so we found the contradiction, which stems from having assumed that every function is computable.